Hello, everyone. I am Teodora, and I'll be here as tech support during the tutorial. I want to introduce you to our first tutor, Kristina Host. Kristina is a research and teaching assistant at Faculty of Informatics and Digital Technologies, and she will hold the Google Colaboratory and Python Deep Learning Basics for CV tasks. Enjoy.
Thank you. Hi, everyone. Please, first, in the chat, you can find the link for the materials. So please click on it and download it on your computer. And then we will start. Did you find the links now? Okay, good. Okay, so in this map, I will put also the script when we are done with everything. So now inside you can find this presentation that is shared and a working script, which you will put in Google Colab to do some exercise. And when this tutorial ends, I will put you also all the code and everything that we have done today. So if you're like, you cannot write something, it's okay, you will have the materials afterwards. Okay, so let's start. Our topic is Google Colaboratory and Python. So we will do some deep learning basics for computer vision tasks. I am from Croatia, from Rijeka. I'm a PhD student and research assistant at the Faculty of Informatics and Digital Technologies. And I'm working on some projects that are related to automatic recognition of actions in sports. If you are interested in projects like this, you can contact me and maybe we can arrange something to work on together. And now let's go to what we will cover. So first of all, I don't know if all of you are familiar with Google Colaboratory, so we will do some introduction in it, how to connect to virtual machines, enter some text, system comments, and similar. This will be a quick part at the beginning. Then we will talk about how to load and use library for images, how to display an image, modify, and similar. That's like the second part. The third part, it will be to create a simple convolutional neural network with the background, what is a convolutional neural network, how to create a model, what are like the basics concept that we have to use, and how to train test the model. After that, we will try an example with transfer learning, where we will use pre-trained models. I will give you one example of YOLO pose model, but I think we will not have time to run it, so you can run it at home with the clip that is also in the materials. And also I put you there some useful links where you can find pre-trained models on different models that are available on the internet. Here are the libraries that we will use for some Python basics. We will use OpenCV, Matplotlib library for showing images and similar. And two important one that we will use for convolutional neural networks are TensorFlow and Keras that allow us to train large neural network models. How? Because it distributes calculations to hundreds of multi-GPU servers. Keras is also for the deep learning task and have an implementation with TensorFlow. So this is what we are going to do. I hope you will learn something new. So let's start. Just check if there are some questions. No, it's okay. Okay, so what is Google Colaboratory? Is a Jupyter environment that is made from Google. So it's a free Google platform that offers Jupyter notebook environment. What you need to have is a Google account to sign in and use it. Here is the link for it, or you can just write Google Colab in your browser. And this is some basic steps if you will need it, how to use Google Colab. So Google Colaboratory allows you to write and execute Python in your browser, and you have access to GPUs and TPUs free of charge. Also, you can use R if you are familiar with that language, but we will do it in Python. Okay, so let's open the first parts. So the working script. Okay, so just write Google Colaboratory in your browser. And if you have to sign in and upload this library that I have given to you. So go to, I will change the language. Go to upload and then browse and take the script that I have posted. So go to Google Colaboratory and then go to your Gmail account and upload the script in your environment. So this is how it looks like. Here you can, in file, open new notebook, an empty one. You can upload it, rename, move, save a copy in Drive and similar. You can also download it here. Once you finish into your computer, you can you can insert code, have some help with, where is it? Search code snippets, some also already done codes that you can use. But what we are going to do first is go to runtime and change runtime type to be GPU if it's not for you, so we can run afterwards the convolutional neural network. Okay, here is the table of content. So every time we have a heading, it will appear here. So you can see what we will do today. Here you can find the data that you are using. So please, after changing the runtime, connect to the virtual machine by pressing here. And then you will see the data that you have here, for example. What is new in Google Colab is that Gemini is implemented in it, and it can help you write the code, so it can be useful. And you can also ask him questions here. Just allow it to help you during writing. Okay, so this is a new feature that is from, I don't know, 2 months ago, I think. Okay, I hope everybody has their script open. So we can start. First of all, if you want to add some code and text, just put between already made lines, and you just press on plus if you want to start coding or if you want to write some text. I will delete it now because I don't need them. Okay, so if you want to install some packages or run some normal, for example, system commands to check, for example, the version of Python or to install something, you will write one exclamation mark and then pip install something, or it's the same thing like you're doing in command line on your computer. So let's now just check a Python version. What is it? So this is how we write system commands. When we are writing Python code, we are just writing it without anything in front. For example, A equals to 10, B equals to 20, and we want to write A plus B. And we will get the result. What is useful here in Google Colab is that you can connect with your Google Drive. We will not use it here, so we can maybe skip that part, but I have put it here. So you will press this on Drive, or you can go in code snippets that will so help search code snippets, and you can find here some already written code. And for example, if you write disk mount cloud storage, for example, this, you can insert that code just by clicking insert. So you can go to that part, and then you have to agree with everything that that you want Google Colaboratory to make change on your Google Drive. So for example, to save file and similar. This is very useful when, for example, you are like taking some code from GitHub, and then you can want to run it and save all the results, because this is the environment that once you exit it, you will lose everything. So always is better to save the results on your Google Drive, so you will then use that part. So you can, if you want, also upload some images, clips, and similar to your environment like this. So for example, if you are going to run the YOLO part, you will go to upload and upload the clip here if you want. Okay, so that's how the environment looks like. And now we are going to do some Python basics for images. So first, let's go with the help of code snippets. If we are writing image, so we have like this part showing images. And we can find here the code for that part. So for some basics, like showing images, camera capture, and similar, you can, in code snippets, already find the code that is for that part. So you can see, sorry, I haven't positioned it good. So I will put my mouse here. Okay, so here is an example with a library called OpenCV. How to read an image and show it. When you're doing in Python on your computer, you can easily also use the cv.image_show to show an image, but in Google Colab for some reason is not working. So you have to use this from Google Colab patches to show an image. This function is retrieving from this link the image and saving it into environment as logo.png. Okay, so this is our result. This is if we are using OpenCV. Let's go to try another one. So we will download this one and save it as image.jpg. You can see also that here in the files now appears the image that we downloaded. So after running this one, if you are refreshing, we have also in our environment the image.jpg. Okay. So let's import another library. So we have here the example of OpenCV. So there's a lot of different libraries that you can use to show images and make changes of them and similar. So one of them is OpenCV and one of them is Matplotlib library for visualization and reading the images. So we can try that part. So how we are importing libraries. So we are going to write import and matplotlib libraries. And now if you activated Gemini, it will help you write the code. Once it proposes something, just click on tab and he will automatically finish the line. So the structure is import something, or from a library, import a specific function. This example is if you want to have a shortcut for a library or a function. So for example, this is usual one used for Matplotlib library for the visualization part. Okay, so if you run it, we will import the library. In the variable called image, let's read the image. So we have this one. So ELT dot, to read an image, we have a function called imRead. And in the brackets and with these things, we are putting the path to our image. So if you're not sure, for example, you can go here to the dots and copy the path. If you're not writing anything, it's in the folder that you are located, so it's in the content. So if you're like, it's the same thing. Okay, once we have uploaded it and read it, we can show the image. You're now writing the variable that we have, and we can define if we want to show the axis and similar. For example, we can exclude that part. And once we have finished everything that we want to show on the image or in the graph and something, we have to put this show function at the end. So let's see. So this is the image we will work with. If we want to find the shape of the image, we can just easily write image.shape. So we can see that the height is 1350 and that we have the width that is 2000. This one is the number of channels, so we have colored image, so we have 3 channels. When we are doing a machine learning task, we have to train our models with a lot of data. Sometimes for supervised learning task, you will not have enough data. And if you're working with images, some little change that you are doing on the image can influence a model, because a model can be then more flexible to some changes that can occur in the images. And it will, for example, easily do it images that have not seen yet. So how we can modify images? We can resize or scale images, we can rotate, translate, we can do some erosion, dilatation, blur, shear, change brightness, contrast, crop, a random cutout, some pixels from the image, do some hue shift, saturation shift, we can add noise, change perspective, and other. I have listed it here, so you can easily search for them. We will pass now through a few of them, how they work and what they're doing to see the results on this image. So this is an example how you modify one image, but if you have a training set, you will have a loop that goes through all image and then augment your data with it. Okay, so the first one we have is resize. Why we can resize images? So we are resizing images because it allows models to be trained to become more robust to change in object size. How we are doing this, or maybe also when you are using transfer learning and you are starting with some model that has an input of a different size, you have to change the size of your images to be compatible with the model. This is when you have to use this resize also. For example, this function from OpenCV uses interpolation for estimating new pixels. So we can use, for example, linear or cubic interpolation. You have also other options, but for example, linear one, to estimate new values, take into consideration 4 nearest pixels, so above, below, left, and right, to create new values. So if you are going to enlarge your image, this part is really useful. Okay, and also you can use the cubic one that uses 16 pixels, but is slower in that case. So let's start, let's try. So we have here an image that is 1000 by 2000, and we will resize it with interpolation to be bigger. So we will use the function resize. What we will resize? We will resize our image on which dimensions, so in larger dimensions, and we will use here linear interpolation. So let's see. Now our shape change, and let's see the picture. Okay, so second, we have trouble with the cable. Okay, so we obtain a new picture that is precise to the shape we want, and the pixels are estimated with linear interpolation. Okay, so there is another example where we want to randomly resize, but with cubic interpolation. So we can run that part. So we'll randomly generate a number between 0.7 and 1.5 to rescale the image to be smaller or larger from the original size. If we are like specifying the scale, then we are not putting the main dimensions, but we are putting none, and then he will estimate what will be the shape after that. Okay, other change that you can do is rotation, for example. So you have some already made function for example, horizontal flip, vertical flip. If you need that, you can see that that's change. You can also have some functions like rotate for 90 degrees, for 180 degrees, and similar. But for specific, for example, 10 degrees, 8 degrees, or if you want some smaller, you have to have another approach that is called affine transformation. So you can use this, that is a mathematical operation that preserves straight lines and relative distances. So images can be rotated, scaled, translated, combine. You can combine all of this, and you will maintain parallelism in this case. So, for example, if you put an angle of 10 degrees, you define where you want to where you are going to rotate the image, for example, in the center, you can create a rotation matrix and then apply this affine transformation to obtain a new image. So you can do with this a lot of changes on the image and maintain this parallelism. So you can create matrix that is with the same scale that rotates by the angle of 10% in the center. And then you can apply that rotation matrix on the image, and you want the final result to have the shape like the first image that you are working at. So let's run that part and we can see a rotation made here. If you want to save your data, if you're using Matplotlib library, you can easily do it with image save, and then the path where you want to save it, for example, your drive, and then the name of the image and the name of the variable where is saved the image that you have done. So you can find it here. Okay, so you have some more examples here. So we have shearing, that is a geometric transformation that changes the coordinates of the pixel in an image in such a way that each pixel is shifted horizontally or vertically in proportion to its position. So you can define the shear factor and how you want to change it. Also, you have to use this, like in the previous example, you have to create a matrix and then to use this repaffine. Some more examples are erosion and dilatation. Erosion is a process that reduces the size of bright objects. Is, for example, interesting to use to remove some small areas or boundaries of objects so you can reduce their size. This is like when we are using erosion. And dilatation is doing the opposite, so it increases the size of bright objects in an image. So it's useful for example, connected some isolated white areas or thickening the objects in the image. How it works with something called kernel. Is usually a really small matrix by 3 by 3 or 5 by 5 that goes through the image, slides over it, and do this thing called erosion. So let's see how it looks like. For example, we define that we want a kernel to be 5 by 5, and we want to go through our image and do the erosion, so to reduce the bright objects. So if we have like here 3 iterations is maybe dark. So you can see here that we have a small change, that we have a darker image. It was 3 here. Okay, so the opposite is with dilatation. So we will increase the white pixels. Also, what you can do is blurring the image. It also uses this kernel, but the idea is that the central pixels are more important than the one that are at the edges. So we can also, for example, here is an example when we randomly choose if it's 3 by 3, 5 by 5, offs, or 7 by 7, and we are implementing a Gaussian blur on our image. Okay, so these are some methods that you can use to augment your data. You can find here other methods that you can use. You can try them at home. This was just an example to see what you can do. Does anyone have some questions here, or we can go further? Okay, let's continue then. Okay, so when we have supervised learning, we must have a lot of data. One of the most famous data set to get in touch with computer vision is this one called CIFAR-10 dataset. So if you are new, you can use this one, the other one called MINST, where you have numbers to classify, or clothes. So this is like the three more basic one to start with if you are doing the convolutional, computer vision tasks. So how this dataset looks like? We have 60,000 colored image that are 32 by 32 pixels. And each of them is divided in a set. So we have a training set that is used for learning, and we have a testing set on which we are testing the performance of our model at the end of training. The shape of our images is 32 by 32 by 3 because we have colored image, and we have 10 classes that has images of airplane, cars, bird, cat, deer, dog, frog, horse, ship, and truck. Each image is marked with a number from 0 to 9, representing one class. So in total, we have 10 classes, and for each class, we have 6,000 images. This is how it's labeled. These are the true labels with words. And what we will use is this one-hot encoding. So it has zeros and one for the category that we are looking at. For example, we are using that because it's useful and expressive, and we can rescald easily if you have more classes, or for example. And why we are using it? Because you can easily then determine a probability for every class. You will see it in the example that we will do. Okay, so this is the data we will work on. And now let's go to convolutional neural networks. What are convolutional neural networks? So you can see this image. This is like an example how it looks like. So convolutional neural networks are a type of neural networks that are specified for the task of for various tasks of computer vision, such as image classification, object detection, and similar. They're specified for images and spatial data. So we will do some classification on images in our example. How they look like? So we have an input layer that is our input images that we are giving to our model to train. We have output layers, so this is called input layer. We have an output layer at the end that has the probability of a class that can happen. For example, in this image, we have a deer that is the model sure 94% that is the deer in the image, but also maybe 0.1 it can be a dog or it can be a cat and similar. So we have an input layer, we have an output layer. This in the middle, it's called hidden layers. And in convolutional neural network, we have different convolutional, so we have convolutional layer, polling layers, and fully connected layers. What's the idea behind it? So when we are using convolution, we want to find features in our images. So how the structure looks like? So we can have one or more convolutional layer. After that, we have to resize these feature maps that we obtain with the convolution. So we are trying to find features with the convolution, and there are like, they consume a lot of memory, so we have to pull it, and then we can use again a convolution, a polling layer, convolution polling layer, and so on. And when we want to finish, when we want to classify our images, then at the end we are using fully connected layers. So first we use convolutional layers and polling layers to extract the feature, and then we are using fully connected layers to classify our images in our categories or classes that we have defined. So this is an idea. How the convolution works? So we have filters, convolutional filters that convolve with the image. So also they slide over the image and are computing some dot products. So they are smaller size than our image that is in the model, but they have the same depth. So if we have a colored image, the filter is also will be in 3 dimensions. Okay, so that's the basic idea. Like it's the same thing like the kernel that we were using for dilatation and erosion, for example. So filters contain the weights that the network needs to learn. There's smaller special units than the input images, and each layer, convolutional layer, usually consists of several filters. So the more filter we have, more features can be recognized. If a filter is activated in some place, that means that some property is recognized. For example, one edge is recognized, or a certain, I don't know, maybe circle, or some feature that you have defined that you want to find. So, for example, at the beginning of the neural network, for example, convolutional neural network, you can, for example, in the second layer, you can find some basic contours, edges, some most basic shapes as angles, circles, and similar. Deeper you go into the network, you will find some patterns, and then maybe deeper you go, for example, you can find some little objects, for example, wheel of the car or the head of a dog, and small parts that are important to detect a final object. So in the first layers, you have some basic features like edges, contours. Then deeper you go, you have patterns. Then you have some, for example, parts of the image that are recognized to be an important part of the final one. And at the end, it can recognize specific shapes that we want to classify. For example, this is a deer, this is a dog. How we can activate these filters? To activate that filter, so we can use activation functions that decide whether a particular neuron is activated or not. So if some specific feature will be found or not. So we have to use activation function, because if we have to introduce nonlinearity, if not, it will be just a regression model. So you can see here, these are like the most famous one. We will use this one called ReLU, that is 0 if negative, and then if positive, it increases. One more thing that is important when we will define our convolutional neural network is that if you look at an image and you have a filter that is 3 by 3 and you are sliding over the image. If you are looking here, this pixel at the corner will be taken into consideration for convolution just one time. If you have, for example, one edge pixels, it will be taken in consideration 3 times. But if you look some middle pixels, if you are using this 3 by 3 filter, you can see that it enters in convolution 9 times. If you want to give also, if you want to include this corner and edge pixels more into convolution, because maybe something important can be also at the edge, and you want to detect that part also, you can use this thing called padding that adds zeros around the edges on the feature maps, so that this corner and edge pixels can be contribute also to the transfer of information. So you want them also to be part of the convolution. So this is padding. And one more thing is pooling. So when we are doing this convolution with filters and then activation functions, we obtain feature maps. Then we want to pool the size of these feature maps to reduce the resolution. How we can do that? We have 2 more famous methods. So one is average pooling. So for example, if you have 2 by 2, you can take 2 by 2 filters to do the average pooling, and you can choose the stride. This is for how many pixels you will move horizontally and vertically when you are doing the pooling. So we want to use, for example, the average pooling. We will find the average of this. Or if we are using maximum pooling, we will find the maximum value in these 2 by 2 parts. So here will be 6, Then we are moving for 2 pixels, so we have the stride of 2, and then we do again the pooling thing here with our filter. Okay, so these are the basic concepts that we need to do our convolutional neural network. And this is the architecture that we will create. So we will have our input images of 32 by 32 pixels. Then we will do 2 convolutional layers, a max pooling layer, then dropout, convolution, max pooling layer, dropout, and then fully connected layers for classification. So in this part, we are extracting the features, and in this part, we are classifying them. Softmax is activation function used for classification. Okay, so let's start. You can now go back to the script. So we will use the dataset CIFAR10 that is used in a lot of you have it in a lot of libraries, also in Keras dataset. So first of all, we will implement TensorFlow, import TensorFlow and Keras, and we will load our data. So let's run it. So the data is already split in train and test variables. In the X part, we have the data, and in the epsilon part, we have the labels. Why we are taking train and test data? So when we don't want to overfit our model. So if you are like training and testing on the same data, you will overfit your model, and it will not have good results if you are putting some images that it haven't seen before. So when you are testing your model, you should keep a part of your data away and just test on it once you are done with training. So let's just check the shape. So we have in the train 50,000 images, and in epsilon train we have 1 dimension, so we have only the label. For example, you can also, if you want to just write the code, just go to this plus. For example, epsilon train, how it looks like. So we have numbers that specify our class. So let's print the class of the first image. So our classes are saved in epsilon train, and we want to see the first value. So our indexes goes from 0. So the first one will have the index 0. So the class of the first image is 6. Let's show that specific image. So X train of 0 with the index 0. So we have here a picture of frog that is 32 by 32 pixels. If you want to show the first, for example, 5 images, for example, in a range from 0 to 5, the last one is not included, so it goes from 0 to 4. Go through a loop and show the first 5. 1. This means 1 row, 5 columns, and first position. So let's show the first 5 images. So we are having the loop, so we are using this. So we can see here how our images looks like. Okay, we will use one-hot encoding. We have a function that do that thing. So keras dot utils to categorical, and we have to define. So we have the train set that we want to move to be like this, and we have to define how many classes we have. So we have 10 classes. The same thing that we are doing from the train set, we have to do also for the test set to be equal. So and let's show, so we have now 0s and 1 for each picture. Okay, one more thing that is important is data normalization. So what is this? Is when you want to put your data to bit, for example, between the value 0 and 1, in order to improve your model to be faster, and it's easier for him if there is not a wide range of values. So if we have different ranges, then we will have this process called data normalization to have a similar data distribution for every different feature. For example, in our case, the pixels are from 0 to 255, and we will put them to be between 0 and 1. So we will normalize our data. So X train, and we will use this as type float, so we can divide and obtain results that are good. So we will divide and have float values after that. And let's then show how our values looks like now. So at the beginning, we had from 0 to 255 the values for each pixels. And now we have from 0 to 1. So this part is called data normalization. Okay, so we have preprocessed our data, and now we can create our model. So this is the architecture we will create. First of all, we have to define the model. So let's call it model. And we are using this one sequential that is we will add one layer at a time, so layer by layer. Just pay attention to not run more times some layer, because the model will just add more layers that you have to. Okay, so first we defined the model, and then we can add some layers. How we are adding layers? So model dot add, and then we can go to keras dot layers convolutional 2D. So we are using convolutional one. And here we are defining how many filters we want. We want 32 filters. Then we are defining the kernel size. So the filter that we are using in the convolution, that is 3 by 3. We have to define the activation function, that is relu. And in the first layer, always you have to define the input shape. So it's 32 by 32 by 3. So this is our first layer. The second layer is also convolutional layer, convolutional 2D. But in this one, we don't have to put the input shape because the model takes it from the previous layer. So we have two convolutional one. Also, what you can put here, it's the padding. So we want to add padding here. So just add padding so that it gives us zeros around the activation feature maps. We want it also here. Also, what you can put is stride. It's by default by 1, but you can also change that. So strides are 1 by 1, so it will go one for 1 pixel horizontally and vertically when it's doing the convolution. So it's good 1 by 1, so you don't have to write it down. Okay, so this is our first two layers. After that, we are having a max pool layer. So model dot add, so keras layers. And we want a max pooling one with the pool size, filter size 2 by 2. After that, we have to use a dropout layer. What is that? So in each pass during training, we want to leave out a certain percentage of neurons. So we are discarding a certain percentage of neurons in order to be less sensitive to changes in input data, and in that way prevent overfitting. So we are taking randomly, in this case, 25% of our neurons in our network and leaving it out. In this way, we will prevent overfitting. Then again, we have convolutional dropout and similar, but with more filters. So we have 64 filters here. So model add. So we have two convolutional one, but with 64 filter number. So we are increasing, deeper we go, we are increasing the number of filters. After that, we have again max pooling one, and then a dropout one. And now we are done with the feature extraction. And now we want to use the fully connection one for the classification part. How we are doing this? When you have a normal neural network that is not convolutional, we have only fully connected layers. That takes as an input 1D vector, so one-dimensional vector. So we have this function called flatten. That is flattening our input, our features that we have instructed here, and put it in a single vector, 1D vector. So we can use this function to do that. And then we can use the fully connected layers that are called dense. Also, we are increasing the number of neurons. So here we have 512. After that, we are using again a dropout layer. And this part is important. The final layer have to be with the number of neurons, how many classes you have. So if you have 10 classes, we will have here the number 10. If you have 100 classes, here will be 100. So this is the last layer. In the last layer, we are using softmax activation function that is used for classification. Once you have written that, you can run it and maybe show the structure of the created model. I will wait a second. Okay, so here you can see the architecture that we have created. So let's go to the compile and train and test part. So when we are compiling the model, we have to define the loss function that we will use, the optimization method, and what we want to monitor, for example, accuracy loss, and etc. So let's write that part. So first of all, we will define the loss function. So if we have a lot of categories, we will use categorical cross entropy. Okay. Then we will define the optimizer. For example, we can use Adam optimizer. We don't have time, so if you want to go deeper in this, please do it on when you have time. And here you can put all the metrics that you want to monitor. For example, we will monitor accuracy. So we have categorical cross entropy, optimizer Adam, and matrix accuracy. There is a comma missing. Okay, so this is how we will monitor our training, and now we have to define the training part. So first, what we have to define is the data that we are using for training. Then we will have to specify the batch size. So this is the number of training data using during one iteration. So for example, how many samples that we are working on before we are updating the weights of the model. So the best is to use 32, that is by default. But if you can also higher that number if you want to be fast, if you want to train it faster, but you will have some worse results. So in each epoch, we are evaluating our model on a validation set. So we are taking a part of a training set away, and after each pass through the network, we are validating our performance. And that we are doing on a number of samples that are defined with a batch size. Then we have a number of epochs. So this is a number of complete passes through the training set, and it can be from 0 to infinity. So from 1 to, not from 0, from 1 to infinity. You can run the algorithm for as long as you like, but you have to think about overfitting in that case. Okay, so in every machine learning algorithm, also if you're like doing linear regression, logistic regression, for training the model, you have this function called fit. So this one. Okay, so first of all, let's define the data. So we are doing it on X train and in epsilon train 1 hot. Then we can define the batch size or leave it. So 32, we can train for 10 epochs, maybe put a little smaller value so we can finish our script. And let's run it. So we have defined the training data. We have defined the validation data. So to take a part of our training, 30% of our training, to validate how good our algorithms perform. If you will put here more epochs, you will obtain better results at home, but to be faster, just put 5 epochs so we can see our result. Okay, so here you have accuracy. This accuracy is on the same task that you are training. So accuracy on the training set and loss on the training set. And this is validation accuracy, so it's on this validation data when you are like checking the performances of the model. So you can see that the accuracy, it was 55%, and after training for 5 epochs, it's 71%. So it increases, and the loss decreases. So if the loss is decreasing, you should train more because your training is going well. Once the loss is increasing, not decreasing, you have some overfitting, and then you should stop training. So you can see here, if you press, you can see a visualization. So our loss is falling down and our accuracy is rising. So we should train a little bit more to obtain better results. But let's go to pass the entire script. So if you want to save the model, you can do it by model save with the chars .chars at the end. And when you want to test the model, you have to use this model evaluate, and you are evaluating on the test set. So this was on the training set accuracy and on the validation set. But what is important is in the testing set. So we have X test and Y test 1 hot. And we obtain here that the accuracy is 71% for our test set. In every model, linear regression and similar, if you want to predict values, you use model.predict. So let's predict the values for X test. And let's see the first one, how it looks like. Because we have one hot encoding, we can see here that we have the probability for every class. What we want to find the highest value. So we will use this function argmax that finds the index of the highest value here. And then we can visualize that, for example. Epsilon spread now looks like this. So we have for every pictures, what is the highest probability, for example, to be a certain class, and we select that part. This we need just to visualize. So in this classification report, you can find everything: precision, recall, accuracy, and other metrics that are interesting. So you are writing first the test and then the predicted values. And just write here class names. So we don't have numbers from 0 to 9, but this names. So we will obtain for each class what is the precision, what is the recall, what is the precision and recall overall, what is the accuracy, and here is how many classes how many samples we had for that classes. Okay, let's also do the confusion matrix. So epsilon test and epsilon spread. So we can see here how many matches we have on this and how many misclassification we have and for which case. For example, for the airplane and ship, we have here predicted that for the case of airplane, we have 139 ship predictions. So here are the true labels, here are the predicted one. So if you have to analyze your result, confusion metrics are really good to see where your model have trouble and where he is confusing. I will clear the output. Also, you can test it on your own image. So just let's run this part. So it's not an image from the data set. What you have to do is resize to be at the same size as the model input. And then you can put it and test it on our model. So for example, we have here an image of a cat. And we can also show it, maybe. Okay, for example, this one, we have to resize to be 32 by 32 pixels, and then we can predict on it resized value. For example, here it defines that it's a frog, for example, 50%. But if we will train more the model, we will have better results, because I know when I am training for 10 epochs, it will be a cat. So we have to train more. Okay, what is when we are using pre-trained models? So there is a lot of data that is available online. So we have big data sets that are available online. And for that, that are already pre-trained. And we can use that part to use that weights and then fine-tune it for our case. What is important step in data preparation for that part? First, we have to resize the images to be as the same input as the network expects. And we have to pre-process the data as is, for example, defined. For example, we can define X-train here. In this part, we will take just a little part of a CIFAR dataset. So we have to resize the training part. And we have to pre-process it how the network expects. So we have this pre-process input function that we have imported here. And for the epsilon, we can use, again, this two categorical. And we have then plus. Okay, so what is transfer learning? So we are using the weights that are from a pre-trained network, but we cannot use the final layers that are used for classification, because these data sets are larger than ours. So we have, I don't know, 1,000 of images if it's pre-trained on ImageNet, 1,000 of classes, but we have only 10 classes. So we have to remove the classification layer and define our classification layer to specify our 10 classes. So we have different number of classes. So ImageNet consists 1,000, we have only 10. We will remove the classification layer, so we will use this include top that is false, and then we will add new layers as we want. but we have to be careful to put 10 in the final layers because we have 10 classes. What we are doing, so we are freezing the layers in our base model so we can use the pre-trained weights. And then we will train additionally for the specific one that we added. One more thing that we can use is early stopping. So for example, you define that you will train for 30 epochs, but if our validation loss, for example, does not improve, so decrease, for example, for 3 epochs, then stop training and take the best model that was before that. So this is like the idea. So let's load the model. So let's call it base model 2, for example. And we are taking ResNet. We will take the weights of ImageNet. We will not take the top layer for classification, so don't include it. And we have the input shape of 224 by 224. That is the input shape for ResNet. So here we change to be 234. Then we are freezing the layers of the base model. Base model 2 with this dot trainable. So in this way, we will have the original weights. And then we can create our model, for example, model 2. It's a sequential like before. And now we are adding layers. First of all, we will add our base model that we have defined here. And after that, it's useful to do a pooling, but it's called global pooling with after doing the base model. So layers dot global average pooling. We can then add some more layers if we want. For example, one more dense layer. With the activation ReLU. And after that, the final one called also fully connected for the classification where we use softmax. The compiled part will be the same. What we have also here to define is this early stopping. In the early stopping, we will have to write what we want to monitor. So we want to monitor the validation loss for 3 epochs. If it didn't change for 3 epochs, then return to the best results before that. So let's put here also 5 to be quicker. And let's see how it performs. After that, we can visualize our base. I have a grammar here. I didn't run that code for pre-processing. So after, okay, I'm having trouble with the GPUs. Okay, it's okay, but I have to run again this part. Maybe this part for testing is not important, but okay, so after data preparation, we can run the training, I hope. And see the results. While it's running, I will show you what you have also here. So I put you here to try at home, for example, the person detection using YOLO. So you can install and then test it on the clip that I give it to you. So it will look like this. So he will find person on the image and give them the ID, and also you can see that we have some key points like nose, left eye, right eye, and similar. And also what you have here is this model zoo, where you can find different pre-trained models. So on Model Zoo, you can change for which framework you want to, in which framework you want to do, for which categories. And then you can find different models that you can use for your specific task. Also, you have from PyTorch the Model Zoo that also can be used. So you have here AlexNet, ResNet, and other. You can use also the TensorFlow Model Zoo. So that is, here you have the link. You have also RoboFlow, when you can find different models, for example, YOLO, Vision Transformer, and similar. So here are the useful links that you can use, and I'm again out of memory, so I cannot run that part. I think the problem is maybe here there's too much to process. I will pass one more time, but I'm not sure if I'm out of memory, there is a problem. Okay, now it's training. I hope it will train it. Okay. So if you're like, so we are training for the same 5 epochs like before, and you can see how the accuracy goes. I hope it will work for me. I'm also maybe having trouble with internet, I'm not sure. Okay, so you can see that now the accuracy for training is so we had here from the start 0.3, so 30% in the first epoch, and here we have in the first epoch 48%. So when we are using some pre-trained model, we have a higher accuracy with only 5 epochs. We have here 84% accuracy. So this is like the privilege of using pre-trained, so you don't have to train them from scratch and you will obtain better results. So this is one idea. So you can see here that we have like almost 100% from the training set, and this is for the accuracy for the validation set is 84%. Okay, so that's it. This is how you can use your pre-trained models. This is one example. So you have here the YOLO to test it. Just upload the clip into the environment and then you can run it. Also, if you want to save the results to the disk and then run it there, it's easier. You have to connect then to your Google Drive. And you have here the model zoo. Okay, that's it for me. I will put you the code, the final script in the map so you can download it. Okay. Okay, if I have any academic papers on this topic. Okay, Jovana, if you will, can you send me an email and then I don't have maybe published, but I can maybe give you some from my classes. But just write me an email on kristina.host@gmail or Unity. You can find it in the presentation. I have my papers that are on handball action. Maybe they're more difficult. So there is also a good book that you can use is from O'Reilly. So O'Reilly. When you can find everything about machine learning. Okay, if that's it, thank you all for participating in this. If you will have, it's possible to reshare the link. Yeah, we can do that. Just a second. Okay, is this one? Okay. So if you have any questions, I will be at the conference. If you find me, you can ask me then, or you can email me and we can arrange a meeting. It's okay. Okay, thanks everyone, and see you on the conference. Bye.